In this video, we're going to look at some different examples to do with points and a line. We have a set of parametric equations here for a line and then a plane. So I've just given them some names, named the points A, B, C, so we can refer to them, named the line L and the plane P. So one thing that you want to start to get comfortable with is recognizing, even if you're not told this is a plane, you should be able to recognize that as the equation of a plane. And same thing here, you should recognize those as the typical way that we write parametric equations for a line in R3. And obviously these are points here, ordered triples, A, B, and C. Okay, so in this video we're going to look a little bit at some intersections and determine whether some of these things meet up with each other in three-dimensional space. And so what I want you to get is not only just how to do these specific examples, but how to think through this idea in general, so that when you're looking at other surfaces or other things in three dimensions, you understand how to think about it in those situations too. All right, so we're going to start by determining whether the point A is on the line L or not. Okay, so how would we think about that? Well, so we've got these parametric equations for the line L. We've got our variables x, y, and z, which represent points on the line, and then the parameter t, which may represent time or maybe not. It might just be a parameter. And so we want to think about if A is on line L. So if A is on line L, then it should be true that I get this value for x, this value for y, and this value for z. So let's go ahead and start with that. I'm going to put in the 1, 2, and 0 for x, y, and z. Okay, so at this point I have a system of 3 equations, but only one unknown. So in order for this system to be consistent, I would have to have the same value of t that satisfies all 3 equations. So that's what we want to do to check to see whether this really is true. So if I look at this first equation and I solve that for t, I'll end up with t equals 2. And so what I want to do is check in these other equations to see if t equals 2 makes these other equations true. And you'll see that it makes neither of these other equations true. Right? So let me just look at the last one here. 0 is not equal to -3 plus 3 times 2. All right, so what that means is that while there is a point with an x coordinate of 1 somewhere on this line, that the y and z coordinates of that point are not 2 and 0. So the answer here is no. And here's the work that shows that the point A is not on line L. All right, we can check to see if point B is on line L. Same way, so 4 equals 3 minus t, 2 equals 4 plus 2t, and -6 equals -3 plus 3t. All right, and if you look at this system of equations, if you solve this first equation, it looks like we'll get t equals -1 from that first equation. And you'll notice that when you put t equals -1 into these other 2 equations, that does check. 4 plus 2 times -1 is equal to 2. And when I put t equals -1 into this third equation, that does check. -3 plus 3 times -1 is equal to 6. So there is a value of t that does give that ordered triple for that line. So in this case, our answer would be yes. All right, so the overarching idea here, though, is that when we're looking at intersections of points, lines, planes, surfaces that we'll look at later, really what we're looking at is these equations being true, and often we're looking at a system of equations being true. All right, so for one more intersection example in this video, what we want to look at is whether line L intersects plane P, and if so, at what point? Does line L intersect plane P, and if so, at what point? So the same idea here, we would want to see if this set of equations together with this equation are a consistent system. So we're really looking at setting this up. I've got an x equals and a y equals and a z equals. So we really can just substitute those in for x, y, and z, solve for t, and determine whether that makes our system consistent or not. So we're looking for an intersection point of line L and plane P. All right, so I'm just putting 3 minus t in place of x. I'm going to put parentheses there just for grouping symbols, but they're not really necessary. You can remove those when you simplify. Plus 2 times my y. And then for the z, I'll put in negative 3 plus 3t. All right, so really what I'm solving is this system of 4 equations, 4 unknowns. I've got x, y, z, and t. I'm solving that system by substitution. I substitute it all into one equation. Now I just have one variable here, so we can just go ahead and do a little algebra. Hopefully I don't mess up the algebra. All right, so I just distributed through my parentheses on the left side of the equation, and then it looks like I've got some like terms that I can go ahead and combine. So if I combine the t terms, I'll end up with negative 9t. And I've got some constant terms, so 11 plus 12, so 23. And then subtract negative 11, and so I'll end up with t equals 11 ninths. Okay, so that gives me a t-value where this system is consistent. We really just have 4 equations and 4 unknowns. So unlike these other problems where I had more equations than variables, when I end up with a solution, that should be a solution to the system. You can verify that it makes the equations true. Generally, though, if I'm talking about an intersection of a line and a plane, I might like to have a point, have that answer given as a point. So here we've got a t-value that corresponds to where those intersect, but I would probably like the point that corresponds to that. So we'll go ahead and take this, and we'll get that point. So we'll get x equals, again, I'm just looking at my system of equations here, the information I have, 11 ninths, and putting that in so that I get what I need here. All right, so we'll have x equals 3 minus 11 ninths. So 27 ninths minus 11 ninths, 16 ninths. Hopefully my arithmetic's okay here. Y equals 4 plus 2 times 11 ninths. So this will be 22 ninths plus 36 ninths. Looks like we'll have 58 ninths. And then for z, negative 3 plus 3 times my t value. So this will be 33 ninths, so negative 3 is negative 27 ninths plus 33 ninths. Looks like we'll get 6 ninths or 2/3. All right, so those would be the coordinates of the point that would intersect. Notice that you're not just going to find this probably by trial and error. You really need to leverage those algebra skills to get this answer here. So the intersection of line L and plane P is at this point here. I'll go ahead and write that as an ordered triple, just so we have good notation for a point. Oops, one more coordinate there, 2/3. Okay, so again, the point is not these specific examples, although there's probably some in your homework like this. But the point of this example is understanding how to think about intersections of anything. You're really looking at systems of equations, leveraging your algebra skills to try to determine what values make those systems true, in which case you do have intersection points, or if the system is inconsistent, not true, then there is no intersection between those.